This conference will now be recorded.
Yesterday we left discussing disjoint sets, right? We saw one use case of disjoint set to detect whether there is a cycle in any relationship or not, graph or not, right? Now, how we can implement the same thing? We in that cycle detection algorithm, we saw that we have to merge two sets and we have to check whether any two given elements belong to same set or not. Can't we try doing it with a map? Let's say set 1 is a map, set 2 is a map, or a map of set, right? This set can be a string. If it is set name, let me write. And here can I write a list of all its members of this set, right? Think about it. If we store it like this, let us say this is one set, right? It has 1, 2, and 5 as its members. If you need to check whether 2 and 5 both belong to same set, what will be the algorithm in this case? We require an ulta map, isn't it? That tells which set you belong to. Otherwise, you will have to iterate over all the entries in this map and check in with which key 2 belongs, right? So we can do it. It becomes complex, right? And then merging two set, in this case, 4 and 6. If these are there, merging we can do easily, right? One set you pick and their constituent or elements you put in the list of this, you delete that entry, right? We want to do it optimally. So today let us introduce disjoint set as a data structure. It says that when you are creating a set, all individual element of the set first time belong to its own set, a single element set. So let's say we have A, B, C, D, E, 5 things in our set universe. Only 5 things are there. They say that A, B, C, D, E currently they are part of their own set. 5 sets will automatically get created. We will see the code, right? How do we represent a set? We represent sets like a tree. If A, B, C are part of same set, it will be somehow a tree. In this tree, root will be one of the element, but it can be any element. And whenever you ask which set you belong to, B will say I belong to set A. C will say I belong to set A. A will also say I belong to set A. So we are not giving a new name to a set, right? And in this tree, this is in general tree, any node remembers its children, right? Here it is the opposite way. Any node will just remember who is its parent. So something like this. This is a tree, the opposite tree, where each node is remembering its parent. And for root, parent is itself. So we are saying that this is a set A. If you ask C, which set you belong, this is what we are calling find operation. Find of C. It should return you an answer A. How it will do? You keep traversing up until you hit the root. And how do you know it is a root? Its parent will be itself. Right? Similarly, when you ask B, which set you belong to, B will say, I belong to set A. Here. And then C, this is a separate set in this disjoint sets. D and E, you can say it is a separate set. It is not a binary tree. It can have any structure. It is free flowing tree. And we'll see the advantage of it. But ultimately, DFE, we are saying, because those are part of the same tree, they belong to the same set. And just for identification, we are choosing one element as the representative of this set. So currently we have three sets, A, C. C I should not have written here, whatever, some other character, because disjoint set means there is nothing common. How do we represent this type of tree using already known data structure? We don't want to create node structure and do these things. Each node has to remember its parent. A map, isn't it? Map, why map? Because then asking will be easier, right? Or any array type of thing where each node you are remembering it. Clear? So let's quickly see. Insertion will be difficult. We will discuss. We'll discuss. Let's see. Map of, let's say our sets are currently integers and its parent is integer, right? This map we are saying this is a parent map. What we are trying to do here is how we will calculate first time disjoint set. So first time whenever we are calculating, whenever we are creating whatever A, B, C, D, E or 1, 2, 3, 4, 5 are there, all will belong to their own set, right? So a constructor wise, we will require a constructor that will take, let us say, an array from us, an array of number. What all are going to be the elements of this set? So let's say this, I declare an array. Universe is, for now I'm just giving 1, 2, 3, 4, 5. Right. So, this one is okay. So we got 1, 2, 3, 4, 5. We want to represent that each belong to their own set. What do we do? What entries we store in map? Parent of 1 will be 1. Parent of 2 will be 2. So we go and fill our parent array iterating over this, right? So for each integer element in this universe, parent of E is E. Oh, Java. Parent dot input E comma E. Okay. So this created the disjoint set for us. Currently everything is disjoint. Now we come back to this picture. Then what we have done is 1 is pointing to itself, 2 is its own parent, 3, 4, and 5, right? Now we need to write two more methods, find and union. Find returns you who is your, which set you belong to, right? And set is simply one of the element of that set. So find will take for which element you are finding the set, right? Which set this element E belongs. What do we find? Parent map is given to you while something you keep traversing, right? So easy to understand it. Let's write recursive code. If E is equal to its parent, E and its parent both are equal, then E is the answer, right? How do I write? If E is equal to parent dot get of E. E and its parent are equal, like in this picture, 1 and one's parent is again 1. It means 1, this set is 1. Then we go and return E. Otherwise, uh, find E's parent and keep finding recursively. It will go and keep finding. Right? We should not write this. It is just for understanding. Recursion we should avoid. You can write this code easily in using while loop. Okay. Union method, it takes two sets and it will combine them into single set. So function signature wise, it is taking set 1 and it is taking set 2, right? And it will combine them in one single set. We will discuss this, but let's complete this. What looks like the time complexity of this function? Height of any set or tree. In this case, worst case will be height, right? So worst case wise, find functions complexity is height. Can I say this is big O of height? So later we should try to see how we can minimize the height so that this function performs better. Clear? Now let's worry about union. How do we union the things? When somebody says merge these two things, 1 and 2, they should belong to same set. There are two choices available to us. Let 1 be root and attach 2 in the same. So what we are doing, changing parent of 2 to 1. Right? Now both belong to same set, right? 1 is also belonging to 1, 2 is also. Or we could have done, let 2 be the root, 1 start pointing to it. Both approaches are there, right? For now, let's do one thing. Let's say that set 1 will remain, set 2 will get destroyed and it will get merged in set 1. So how do I write that code? Which pointer I'll change? No, set 1 will remain. Tell me. So let us say this is this and there is another set 3 and 4. Which two sets are there? We called this function with 1 and 3. We are passing sets, not elements. We will never merge elements. We always say merge these sets. Right? Let's say we are doing it like this. Set 1 remains. This was our set 1 and set 2. So what pointer we changed? S2's parent now became S1. So how do I write this? In parent, we will go and update S2. S2 is now its parent changed to S1. Clear? So an unoptimized disjoint set is ready. We are able to merge things. We are able to find which set you belong. Let's quickly test it. Currently, if I ask ds dot find of 3, I'm asking 3 which set you belong. What answer I'll get? 3. Okay. So we got 3, whether we are able to see or not, font wise. 3. Now let's say we want to merge 1 and 3. So ds dot merge. 1 and 3, let's say we know 1 and 3 are parent. 1 and 3 are the set numbers. So set is a number, right? Here set wise, it is just a number. It is one of the element. There is no separate data type for set, right? So ds dot union, we are saying 1 and 3. And 1 and 3, we should ensure that these are sets. These are not any other elements. Currently, I know, but what you are saying is correct. We should do find of 1 and send that. Agree? Okay. After merging this, if I again go and ask 3 which set you belong to, then it will say no. And if I ask 1 which set you belong to, it will also answer. Right? So that way set got merged. So before merging, 3 was 3. Now 3 and 1 both are part of the same set. Right? So very basic, not very basic, almost 75% disjoint set is done. Now let's try to optimize it. We saw that height should be minimized. So approaches wise, this 1, 2, 3, 4 has same height, means 4 height, and 1, 2 is also pointing here, 3 is also pointing here, 4 is also pointing. We are free to create any tree, anything. This looks better, right? You ask this in just one iteration, it will say which set you belong, right? How do we optimize this? Let it be like this, how we did. But what we do is we compress the path as and when it happens. So one was the set. When somebody asks 3 whose parent, which set you belong, 3 anyway traverse this, right? After traversal, 3 knows the answer that my parent is 1. So 3 will say, why I'll have this many links? Let me directly remember who is my parent. And we are doing this on need basis. And since we have written this type of code, recursion wise, this will also go and update parent if there are multiple links. Getting the idea? If somebody asks, find 3, find anyway have to traverse this. And as soon as it's found its parent is 1, for next call, this call is still order of height. For next call, it compressed everything. It says that, okay, my parent is 1, let me remember it. So it will go and update its parent to whichever is the nearest direct parent link. Idea is clear? I'll leave the implementation. It's very easy. You just have to put that parent here in map. Second thing is we try to minimize this height while merging also. Let's see one example. If 1, 2, 3, somehow we created this and there is another set 6 and 7. We discussed 2 choices. This can point to this. Did height changed of this tree? No. Previously also the max height was 1, 2, 3, 4. Even after merging, it is 4. Versus if we had done this. Previously, this set height was 2. Now this is increasing, right? So you see the benefit that whichever the bigger, it should be existing. Smaller should just come and merge in that. That way we are not increasing the height of bigger thing. Idea wise we are clear. So 2-3 approaches are there. You can start maintaining a rank. Whenever something you merge, you increase the rank in a separate map. And based on that rank, you just see which one is bigger. That will swallow the smaller one. So I can, here we discuss that either it can be S1 or S2, right? To decide this, we will decide which one has bigger rank. Simply it can be which one has bigger, which one has more element, right? That will swallow which one has lesser element, right? So combining these two techniques, this is, I can say, union by rank. Combining these two techniques asymptotically, it will almost become constant, finding your parent and all those things. One time it may still take high time, but if you are running it for multiple queries, not asymptotically, amortized way, over a period of time, it becomes constant. Right? And you see this data structure is just 10 lines of code. This is just for understanding. Nobody codes this one also. What we do is we create an array. And in array way, we always know that we can just store 0, 1, 2, 3 type of thing. You can map this to any set element you want, right? This says that if we are putting -1 here, then minus means you are parent. So the starting point of this array will be something like this, index wise. Now you ask 3, which set you belong to? 3 checks its value. Oh, I am negative. It means I am the parent. I am the representative of this set. Minus represents you are the parent. You are the root of that tree. This value can represent how many elements you have inside your set. Now let us merge 0 and 3. So pictorially 0 is this, 3 is this. We can do either this or this way. 3 should remember that now my parent is 0. Right? 3 is now not its parent. It's not the root of this tree, right? So 3 will start remembering, oh, my parent is 0. Simple, right? Now if you ask 3, which set you belong to? 3 checks 0. Again you go and check 0 is -1. It means 0 was the root of this tree and 3's parent is 3 set is 0, right? When you merge this, while merging, you make this zeros count to 2, -2. So magnitude of this minus number is telling how many elements you have, absolute value. And negative is telling whether you are a root or not. Right? Same thing, without using a map, we are able to store it in an array. That's how we use disjoint sets usually. This was just for understanding, but this is also good. Map is a good data structure, fast data structure. Right? Okay, so this was disjoint set. Today's we are going to focus on just two things: shortest path algorithms on weighted graphs and string pattern matching algorithms. Those are algorithms. Somebody has already invented them, right? Somebody has already checked the correctness of them. We just try to understand them, trace them in such a way that it's easier to remember the algorithm. So whenever we have to code, we will code it. Okay. This is a C++ code for a normal BFS in a graph. Breadth first search in unweighted graph. Let's take 2 minutes of time. Map.size is number of vertices. We declared a widgeted array. This slide is simply putting everything zero in the visited array C++ wise. We can write a for loop. Then BFS we do like create a queue. First time we post the start vertex and mark it visited. Right? And while queue is not empty, we take out the front, we print it, visit it, whatever we have to search, we search it. Then for all its neighbors, right, one by one we see if it is not visited, keep adding them in queue. Right? Now we discussed that in unweighted graph, shortest distance is simply whether you are my neighbor or my neighbor's neighbors. We simply do BFS and we will solve the shortest distance problem, right? Clear? So let me see if I have a slide. So in this graph, if somebody asks between 0 and 3, what is the shortest distance? You first search 3 in this, right? Or you simply are maintaining the level. Then next BFS level you saw 3, so 2 times it is at distance of 2, right? If somebody asks what is the shortest between distance between 1 and 6, you will have to start BFS from here, not from 0. Start BFS from here, and then this node, this node, this node are your direct neighbors, right? What is the shortest distance between 1 and 6? 3. And shortest path is 1 to 0, 0 to 2, 6. So when you checked your immediate neighbor, then their immediate neighbors, and then their immediate neighbors, you got this 6, right? So shortest distance in unweighted graph is simple BFS. How do we do it? How do we change this so that we can answer shortest distance easily, and we can also trace back the shortest path, right? What we'll do, we'll create a distance array, and for path, something map or array, it doesn't matter. You just remember who was from where you came, who was your neighbor, who was your parent type of thing, right? That way you can backtrack and check it. So in this, if you see 1, 2, and 4, we added in the queue because of 0. So its parent becomes 0. If we started BFS from here, right? And 3, 5, and 6, for 3, its parent was 1, 5, its parent was 1, 6 parent is 2. Right? Once full BFS is done, starting from 0, we can answer any query 0 to x. What is the shortest distance? What is the shortest path? Like 0 to 6, we are seeing it is at second level, 2. And trace back, go to 6 and check who added you in the queue? 2. 2 who added in the queue? 0. That way you can get the reverse path. You can just print it in reverse and we got the correct path, right? One trick is, if this is undirected graph, if somebody asks what is the shortest distance between 0 and 6, you start calculating from 6 to 0. It will give you reverse answer, right? And reverse of reverse is correct answer, right? Isn't it? So these type of algorithms are called single source shortest path. Even if somebody asked you from 0 to 6, what is the shortest distance? When you run the BFS, after completion of the BFS, you can answer anything, 0 to any other destination. Next time, if somebody asks what is shortest distance between 4 and 6, you will still have to start BFS again, 4 as the start vertex. And then you will be able to answer 4 to any destination. That's why these are called single source shortest path. Clear? So in this, what we are doing is we declared a distance array. Let's say everything is filled with 0 currently. And we will also maintain a parent array. Whatever is the default. Whenever we are adding the start vertex, can we say start to start distance is always 0, shortest distance? So we also go and update here. Distance of source is 0. And parent of sources, let's put something that is not valid, minus. Right? That way, while backtracking, we will stop here when it becomes minus. Here. Now what do we do? Here we are adding something in the queue. When you add something in the queue, you update the distance and parent. So we are here U2, all V's, V1, V2, we are visiting. These are the edges of U vertex. Right? And this is your V1, V2. Don't worry about syntaxes, right? You will access map in Java or this way, right? V1 got added because of U. So V1's parent should be U. And what should be V1's distance? U's distance plus one more level. Agree? So that's what we need to change here. If and only if we are adding in the queue, not for all your neighbors. Right? What do we do? Distance of whatever is this vertex becomes 1 plus distance of U, and parent of the same thing becomes U. That way, and these arrays we should pass from outside, so that once BFS is done, these array we will get filled with the answers. Now if somebody asks what is the shortest distance from S to X, directly dist of X will have the answer. Right? What is the shortest path? Then you start from X and keep checking parent in a while loop until you hit -1. That is the reverse path, shortest path. Idea is clear? And this is the implementation in unweighted graph. We are done. Finding shortest path. But this doesn't work in weighted graphs. Why? Give me an example. Means here, let us say we are finding shortest path between this and this. This weight is 1, this weight is 2, and this weight is 5. And let's have this also greater than 3. So let's say 5. Now when you start BFS from this node, it will say this all are at single distance. Right? But we know that these things will get avoided if we go by via some other route. Right? So weighted graphs. Have we coded any weighted graph problem? No. How do we represent weighted graphs? Map of, so list of list, map, whatever you say. This is our vertex and array list. What did this array list contain? No, in unweighted graph, what did this array list contain? Neighbors list. Can we say this is neighbors list, right? Now this time it will contain neighbors and what is its weight, right? So this is your U, and then this list will have V1 W1 pairs, V2 W2, two things, right? So array list of a pair, or let's have a edge type of thing where it contains two data members, V and W. And that way we have full information, U, V and W. U to V there is an edge, its weight is W. Clear? This picture I have taken from Wikipedia, animation also. So whenever you want to retrace again, you just search Distress Wikipedia, you will get this. Distress algorithm is again single source shortest path. What do we mean? When you run this algorithm, starting from a start vertex, you will be able to answer anything of this nature, this same start to any other destination, once this algorithm completed. But when somebody changes the source, you will have to run the algorithm again. Okay. Now let's trace it with 2-3 example, and then we will see implementation will become easier. Let's say somebody asks what is the shortest path between 0 and 4. Manually, what is the shortest path? Oh, 1 and 4. Yeah. 1 to 4, what is the shortest path? There are multiple paths, we agree? 9, 11 looks like we'll reach in 20. This is 22. This 14 and 9 becoming bigger. 14 we are avoiding, right? Right. So this problem we are solving. This is your source vertex. This is your destination vertex. But when you run distrust, since this is single source shortest path, you will be able to answer 1 to 6 also what is the shortest distance, 1 to 3 also what is the shortest distance. Okay. Now let's see. We will require again 3 arrays: a visited, a distance, and a parent. Ultimately, distance will fill with the shortest distance after the algorithm completes. Parent will fill with the who changed you, so that you can trace it back and actually print the shortest path. So I just change it to 0, 1, 2, 3, 4 because creating arrays with 0, 1, 2, 3, 4 is easy. Right? Oh, I didn't change. Let me see. This is one only. So distance and parent we created one best array. Let's assume distance of source to source we can go and put 0, and parent of source -1. Rest all we put that currently we don't know, a very big number, integer.max value. Parent, even if you don't initialize, ultimately you have to fill everything. Nobody is going to use parent unless you filled everything. Right? One more array is required, a visited, whether it is an array or set, whatever. But you need to remember with which vertex you are done with. Right? In this picture, I have not created, but we will use something called out. Now start from your source, right? And keep going, go and check all the edges coming out of that source. Right? Always remember this. This is U, this is V, and this is your W. From U to V, there is an edge, its weight is W. Currently, from source to source, what is the shortest distance? 0. And how do you know? You go and check this array code wise. So distance of U, right? Now when we are reaching V, right? We already reached U with 0 distance. And if you follow this edge, what will be the total distance to reach V? 0 plus 7. Is it better than whatever we have remembered till now? Yes. So go and update it. And when you update who updated it? One updated. If you don't update, don't update the parent array. Right? Keep repeating this same for all the outgoing edges that you see with this. As soon as you are done, mark this one visited. You are done with this. Now you have to repeat the same process with one of these vertex, right? Here Distras came up with the logic. Start with a vertex that have the minimum distance available, something like greedy. We could have started anywhere, right? But that will not lead to the solution. So in this minimum, whatever is the minimum, not out, we will pick. So let's see. First time it will become 7. So this became 7 in distance array, 7 in parents array, 1. This edge 0 plus 9, 9. It is better than infinity. So update it 9 and parent is 1. Similarly, this one 14 and parent is 1. You are done with all its neighbors, mark it out. And then you have to repeat the same step with one of these vertex. How do we choose next vertex? Min of not out numbers. So what is min of these not out? 7. Which index? 2. And that's why we are starting from 2. So 2 again, 2 has 2, actually 3 edges, but this one is already out, so you can ignore it. Remember, we are always calculating what is the shortest distance from 1 to 3. It's not from 2 to 3. Right? To reach 2, you already know that 7 is the current answer. And then from 2, if you are reaching 3, answer will be 7 plus 10, 70. It's like you are going from 1 to 3 via 2. Right? So this time your edge is this U, V, and W. Right? What all values we are comparing? Current distance of V. What is the current distance of 3? 9. Right? And if we come via 2, distance of U plus this weight between edge of U and V. In these, if this looks better, coming via 2, then update the distance of V and parent. So currently, 3's distance is already 9. If you come via 2, it is 7 plus 10, 17. So we should not update. 3's distance is already 9. 9 means you can reach 3 directly from 1 via 9, right? If you come via 2, then it will take 70. Clear? So we don't update it. Similarly, 2 will check with this. Now, will it update? So 2 already checked this, it didn't update it. This 2 has one more not out edge. Current distance of 4 is infinity. If you come via 2, then it is 7 plus 15, 22. So it will go and update it. Right? So 22 comes here and its parent becomes 2 because 2 updated. Okay. Then 2 is done with all its edges. So mark 2 also out. And next we are choosing minimum 9. So next we will iterate with 3. And that way, until unless everything is out, you can keep repeating it and we will be done. Ultimately, this will be filled, this will be filled with the shortest distance. Now you see, first time we updated it with 22. Some later iteration, it became 20. And we knew that this is the answer, right? If somebody asks what is the shortest path between 1 and 4, go to 4, you come via 3, go to 3, you came via 1, and 1 was the last node. So 1, 3, 4 is the shortest path. Right? If multiple paths with the same shortest distance, and that information we are not storing here, right? It will always remember. Code wise, you can change. If it is equal to also the distance, if you change the distance and parent, you will remember the latest you discovered. If distance and new distance is same and you don't update, then it will remember the first shortest path that was seen by your algorithm, right? Multiple also, you can think, you can start remembering parent array should be a list of something, right? Distance will not change, right? So whatever we discussed, let's quickly see this. We created a distance array, parent array, and visited array. Distance, we go and fill everything with int max. Parent, let's fill with -1. Visited, everything is currently false. Then source distance becomes 0. Parent is of source is -1. Let's write a infinite loop. Go and call a function get not visited vertex with minimum distance, right? We will have to pass the distance array and out array or visited array, isn't it? And this should be easier, right? You have to find the minimum, return its index, and that minimum should not be already marked out, right? So simple array. As soon as you got this u, if you got correct u, if everything is out, you will get, let's say this function is returning -1. Then you can break this loop. If you got any u, go to all neighbors v of u, access its adjacency list, iterate over all the edges, all the v's. If it is already visited, don't do anything. U to v, if v is already marked out, don't do. Otherwise, we have to compare two distance. What is the current distance of v written in the array? And what if we come via u? Via u is reaching till u is written already in the array. And from u to v, the edge will give you the weight. If this one looks better, then go and update distance array with this distance, parent mark it as u. When you are done with iterating all your outgoing edges, then go and mark yourself visited. Right? Ultimately, after each iteration, we are visiting one of the vertex and we are marking it visited after visiting all its edges. Right? So how many times this while loop should run? NV times, number of vertices times. Can I say? So what looks like the time complexity of this code? Oh, we know. Let's analyze. What is the time complexity of finding minimum in an array? N. How many elements are there in our array? NV. Vertex. So this itself is NV. And we are repeating NV. Right? Correct? You see, this thing we can optimize. Finding minimum, how do we optimize? Each time we have to find a minimum and remove it. Next, find the next minimum. Min heap. Right? So basic algorithm wise, this is the algorithm. Very easy to code, but nobody will use it. You go to heap just for optimizing this line. Rest all code will still remain same with some changes. Now overall time complexity of this is V. Let's say V we are saying is number of vertices. This is V, right? What about this loop? For each U, it is going to its connected edges. For next U, it will again go and access its edges, right? So can I say overall for all NV, it is ultimately covering all the edges, combined outer loop plus inner loop, right? So it becomes V square plus E. V square because of these two, and outer this loop and this becomes E. Agree? right? Yeah, Amit, any doubt? Correct. VE, uh, not VE. Why VE? Each vertex we have edges, but this E we are saying is the total edges. For each vertex, let's say this graph. How many edges are there? 1, 2, 3, 4, 5, 6. 6 edges. When you iterate for this, you go and just check 3 edges, right? When you do this, let's say this was directed graph. Otherwise, it will be 2 into E. 2 anyway we can ignore in big O. For this, this is only one edge. For this is only one edge. For this is only one edge. For this, there is no outgoing edge. Let's say if it was directed. In total, 3 plus 1 plus 1 plus 1. You visited 6. It's not that for this, you are visiting full 6. Getting that intuition? For this vertex, you are not visiting all 6 edges, right? Only all edges that is coming out of it. Then for this, only those edges combined, we are visiting full edges. That's why we are not writing V. Clear? And that's what Distras discovered. We have to repeat it, right? First, we went and calculated shortest distance, whatever looks from here, right? Then we have to repeat checking all these things. If you do it randomly, it doesn't solve the purpose. One, we have to cover all the edges. Yes. This one next time we are saying, right? Distress says that pick this, and if I think an example, why we should go to the nearest thing, right? Hmm. Will be maintained, but you are also marking it out, right? Maybe this is the greedy approach, why it is working, because you are marking it out. If you don't mark it out, then anyway you can access all the paths and you will keep updating, right? Then it becomes brute force. Getting the idea? When you marked it out, any vertex, you are not again revisiting it. In brute force, you will again come back via some path. And if you see the new distance is this time smaller, you will update. But here we want to do each vertex one time. And Distrust discovered that next time, if you choose the minimum distance thing, then it works. Do we agree brute force approach will be from here to here, list down everything. Go and keep checking all the path, write backtracking code. From this, one edge goes, from there, whatever edges goes, right? And whatever you see minimum will be your minimum, right? So that's what you are suggesting, right? Hmm. Starting from one, yes, we will update. Yes, yes. No, we are not choosing 7. We can choose anything here. Where you got confused. So from 1, we can go in any order, but we are choosing all the edges starting from 1. No, 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 which is not minimum. Okay. We started from S, whatever S is given. Since our distance array S is the only node that is 0, right? Rest all are infinity at starting. That's why first time we are getting this. For next iteration, when you are done with this 1, next from where you should start? So do you start from 3, doing the same thing, 5? In this case, Dritsa says that choose a vertex whose distance is smaller in this. So let's see. First iteration wise, this one went out. Now we have to repeat the same process with any vertex, right? Distress says that any vertex, it will not work. You have to choose with smaller distance. Let us say this was 2. Then your next iteration you will start doing from here. We will see some graph you can search, but it doesn't work. Algorithms, let's learn. We can we have to come up with an example where it will not work, right? Because here, if you have chosen this, right? Let's say this is 2 and this is 2, right? If you choose this time it will go and update it something like this, right? It should become 4. Distance of this should become 4. Coming via this, right? When you mark this visited and this was already, let's say 1, you have not chosen which one was a smaller, right? You choose any random vertex, right? Once you are done with this, if there is any path that can get it updated, it will start filling it. Because we are also marking it visited. Once it is visited, we are not changing. We know that whichever is visited already out, we know that for that answer is already calculated. If we have to start from any vertex, then you can't mark anything out. So one by one, we are successively finding. After one, when we mark this out, 2 out, we know that its distance is already calculated. Whichever way you come, it will never change. Why? It's a simple intuition, right? From here, you pick the shortest distance, isn't it? Till here, you already reached with the shortest distance. Source to source is shortest, right? If you are able to reach using this link and you picked shortest one, right? Can there be anything else where you will get less than 7, any other path apart from this? Think about it. If let's say this is 1, this is 1, this is 1, this is 1, that can be a shortest path to 2. But then in that case, you may have chosen this, right? So distress wise, it says that if you choose the shortest one, already you got the answer for this. If this was 1, then 1 to 6, this is the shortest distance, right? So mark 6, that okay, 6 wise we are done. Let's complete others, right? This step is making it less complex. Otherwise, it will become brute force. You are visiting all the paths and you are updating distance, even if it is 7. Next time also you are guessing that 6 can also come. Here we are fixed. One time you marked it out, since you have chosen the smallest thing, right? The smallest of the outgoing edges, that is the shortest distance automatically from 1 to 2. Mhm. One first, 2, 3, and 6. Hmm. In a queue. Ah, ah, 6 birds. Ah, hmm. So to understand this, no path will be there that is shorter than this, right? So distrust why it suggested that if you are choosing the smallest, it is guaranteed that for this you got the answer. From here, let's proceed and find other answers, right? Otherwise, you will have to keep doing it, and you will also have to leave it open that from any other path will be there. So complexity will be more, and then it becomes brute force. Longer. No. What he is suggesting, if you try everything, then though you will know the answer, right? You don't mark it visited. If you don't mark it visited, it becomes brute force, simple backtracking thing. Yes. At the end, we will know the answer, right? Yeah. Uh, Yes. Yes. Yeah. And it also becomes complex. So you will have to write something like backtracking. From here, three paths are there. Let me try one by one all those things, right? And keep updating the things, right? And then how do you say that recursion can remember it's visited and all those things, but distrust tries to optimize it. Do we agree we can write backtracking code without worrying about distrust and all those things? It will solve the problem, right? And that's what you are suggesting, right? Distrust says that, okay, once we are, let's say there was some imaginary source. We reached one with a distance 0. Now we have to reach 2. So 0 plus 7 is 7 that way. Can there be any other shortest part if we have chosen next time this is the smaller, right? There will be no. If this was the smaller, then you must have chosen this. That is the inducer, right? So let's see how we will do it with priority queues. We have to find minimum in each iteration. Priority queue, finding minimum, what will be the time complexity? Finding minimum, 1, but correct, 1. And then we will keep adding something also. So let's trace it, which is log. It's too confusing, but so let's say this is our PQ data structure. The algo says that you will still maintain distance and parent array because you have to return those arrays, right, as the final answer. And let's also maintain a visited array or out array. Three things. Then I start from the source vertex. And how do we start? This time go and add in priority queue a tuple, a pair, source, and its current distance is 0. Agree? Source distance is 0, shortest distance, right? This is the current distance. Final distance you will still be updating in the distance array. So source wise, we know we found the shortest path from source to source. That's why in distance array we go and put 0, parent array we go and put -1. Now let's take out this from the priority queue. Obviously one thing is there, it will return you this tuple, and that's why we are starting this neighbor iteration from source. Now let's iterate the neighbors. S to A, shortest distance, the weight is 1. Total distance will be 0 plus 1. Current distance is infinity, right? So we will update it. So this becomes 1. And when you update, this time go and add it in the priority queue. So A added with whatever distance you updated in the distance array. This edge, it will go and add C2 in the priority queue. We are done with all these outgoing edges. Mark this one out. Clear? Next time we have to repeat the same thing. How do we pick? Ask priority queue, give me your minimum weight wise data. And when you take, you also remove it. That's why it will not only be order of 1, you are removing will be log n if there are n elements in the priority queue, right? How do we remove? Replace with the last and then heapify it again. So it will be log n. Clear? Since you removed this, A came to you, you started it doing the same steps starting from A. Now let's do. From A, only one edge is going out. So our inner for loop will run one time. Current distance of B is infinity. If we come via A, 7. A we can reach in one distance and plus 6, 7. So we update this and we add B7 in our priority queue. And we are done with A, we mark it. Now if somebody asks source to A only, what is the shortest distance? You can break your distress algorithm here itself. If you are just interested in solving your problem, not solving all problems. Because A, you will see that it will never get updated. You found the shortest path. Okay. But if you run it, advantage is you can answer many other queries, source to any other destination. So depending on the problem, you can break here or you can keep continuing. Now this time if you ask priority queue, what it will return? C. Let's delete C and start doing the same thing. C has this edge, this is already marked out, so leave it. Don't touch it. U to V is already marked out, visited. This one, it will update. What is the current distance of C? 2 plus 3, it will update 5 and we go and put 5 here. Whenever we update, this time we are also adding it in priority. So ultimately, this is what were the intermediate things in our array, right? And we wrote a function get minimum index. Priority queue will directly give us in log n. That is the only thing we are doing, right? This time, which vertex will come out? D. So now you see B is not coming out. It's not. D comes out. C is already marked out. Yeah. D has only one edge. D till D you can reach in 5 plus 1. So E you can reach in 6. So E6 comes here. Right? And then D also we mark out. Next time what will come? Only B7 and E6 are there. E comes. E doesn't have anything, so your inner loop will not add anything, not do anything. E is also marked out. Then B comes. B, only two edges are there. Both are already out. You'll not do anything. And ultimately, shortest distance between source to, let's say E was the end, is 6. And you can answer anything. Source to D is 5. Source to E is 6. That way. This we should code here. It will give us practice on priority queue also. Weighted graph representation, how do we iterate and all those things. Clear? So algo wise, I have written, so you can just convert that into code. Let's see. We took 3 arrays, distance, parent, visited. We initialized everything and we created a priority queue, and first entry we added ourselves. Source and its current distance is 0. Now while priority queue is not empty, when you remove, since this is the first entry, first time source will come out. So we are iterating, starting iteration from source, and what we are doing is the same thing. Go to all neighbors of U, compare what is the current distance of V and what if you come via U. If it looks better that coming via U is better, Then update your distance array, update your parent array, and this time add this v and distance of v in the priority queue. So from next time onwards, something else will start. Keep repeating it until it becomes priority queue becomes empty, everything is marked out, and distance and parent array will be filled. Clear? Before going to code, tell me the time complexity. How many times this outer while loop will run? Vertex time. Each time we are getting one of the vertex out, right? So this is running v times, right? V, and removing something from priority queue is log v, if there were first case v entries. So these two combined is v log v. Inner loop, outer loop plus inner loop is e, total e times, isn't it? It is not v into e, it is e. Same inner loop is there. But in inner loop, we are also adding something. So it also becomes e log v. So v log v plus e log v, or v plus e log, right? This is better than v square plus, we wrote there, e, right? It is, this one looks linear plus logarithmic, that is anyway. Clear? So let's go and code this, spend 15 minutes of time and code this. Last class today, force refresh. Algorithm is here, you can take help. And code directly the priority queue way, not the array way. These type of questions, they give you in online rounds, one question will be there that is like differentiator question, right? All other questions, many people can solve. This one is like, if you are able to solve after solving those three, it's very good, right? If you picked this question, it will kill your time also. So these type of questions we should do in last itself. So, so there is an edge class. It has v and w as the data member, and compare to is already written inside the class. It is comparing based on weight. So you can directly create a priority queue of this edge, and it will start working. Okay. If this compare to or comparable was not implemented, then you may have to write comparator, and you will compare now based on weight. So last class, first problem, and in the class description there is also a link if you want to open the algorithm. Let's just convert into code. Graph notation is clear. It is like each vertex and what is its neighbors list. This time neighbors list contains two information: who is the neighbor and what is its weight of that direct edge. And this S is the start vertex. Ultimately, this question says that run the discharge algorithm and go and print the full distance array, not a single. We require 3 arrays distance. In this, for this problem, you can leave the parent array. We are not tracing the path, but still, let's complete full algo so we can code it. Have you solved this problem running median of integers? Yes. There we use priority queue, right? So, multiple problems, so we are comfortable. Takes a lot of time, especially if you have to write this comparator and all those things, right? Here it is given. Integer dot max value. This is how we write in Java. Full capital underscore, right? Visited, let me take as Boolean array. It is just true, false. Parent array. But I'll suggest code it so that your algo is ready and submitted, right? If somebody asked, then we can print the path also. In Java, visited initializations would not be required. Just for clarity, I wrote. Otherwise, by default, this will be false. Priority queue, what first entry we had? We have pair, source, and 0. So here, I guess, a constructor is given. Let's use the same thing, v and w, to store it, right? Why to create a separate pair class for priority? New edge, source, and 0. Afterwards, write the loop. So first time source will come out, iterate all the edges coming out from source and keep updating it. Once you are done with iteration, then go and mark it visited.
This conference will now be recorded.
So while priority queue is not empty, we get out something from priority queue, and this will be the minimum pair, minimum by weight. So what I'll get here, whatever by inserted, we inserted edge, so we got E here, right? This E has two data members, V and W. this V becomes our U for next iteration of distance, right? Isn't it? So let's take it in a variable, it will become easier. Int U becomes E dot V, right? And first time, this is S, the start vertex, right? Because we added S and 0, only one thing is there, we removed it, right? We got S and 0 in E. So E dot V is our S. Now here what we have to do, we have to iterate to all its neighbors of U. So how do we iterate? Adjacency list or neighbors list, we have to ask map. So map name is G dot get of U. This gives us the neighbors list. Neighbors of U. Let's put them. So it will actually give us an array list of edge. I'm writing it in multiple lines, so it's easier. So we got adjacency list of U. This adjacency list we have to iterate. It doesn't matter which edge we are going. All edges we have to cover. Right? So for each edge E in this adjacency list, this for loop line 27 to 29 will keep giving us one edge at a time. And each edge has two information. What is the V? What is the W? U we already know here. Right? So in this picture, this is the U, and this will be VW, this will be VW, this will be VW. Agree? If this, because of this U, you updated the distance, you will update parent and all those things, right? And when you update, you also add the updated distance and this V in the priority. Yeah. So just for clarity, I'm breaking it. Int V is E dot, sorry, int E dot V, and W is E dot W. So now we have three variables, U, V, and W. What two distances we compare? Current distance of V and weight coming via U, isn't it? You still have to reach V. Currently, we are discussing from source to V, whatever in between something is there, right? Currently, whether it is infinity, whether it is 100, that is one parameter of comparison. And if you came via U, right? If you came via U, whatever was its distance plus this weight, isn't it? Maybe previously you came via some other route, current distance is 100. If you are coming via U, whatever, reaching till U is taking distance of U, and plus, because you are following this edge, plus this weight. So 50 plus W, or I can write distance of U plus W is one parameter and distance of V is another parameter. If this one looks smaller, then update distance of V. Right? If this one doesn't look smaller, then leave it. This path was already good. Agree? Okay. Minimum code is here, right? See, two things are there, right? Minimum we find to find an edge from where we can iterate to all its neighbors. A vertex from where we can iterate to all its neighbors, right? Now these neighbors, anyway, we have to iterate everything. Once we are done, this is out. Then out of these things, which one we should pick and start doing it? For that, we require finding minimum, right? So coming via u, if this looks smaller than the current distance, we will go and update things. Current distance of v is already written in the array. It may be infinity, it may be something, right? Now, can this lead to integer overflow? Because by default, everything is infinity. Infinity plus something can lead to overflow. Check this code and let me. U is already visited, right? Or U's distance is already calculated. First time, anyway, S was 0. So for first case, it is not. Next time, anyway, you are choosing something smaller, right? So this should not be a case, right? Okay. If we found a shorter distance, let's go and update it. So distance of V, we found a shorter distance. So distance of U plus W, and who becomes the parent of V? U. Because of U, you changed it, right? And in PQ, go and add a new entry, this V, and whatever the new distance you found. So if we see this in terms of this, first time 1, you added this 7, updated it 7, right? And that's why in priority queue you are putting 2, its distance is current distance is 7. Then 3, its distance is 9. 6, its distance is 11. So that next time priority queue, looking at this weight, it will now return you 2, right? One more thing, even if you don't do code works, but it's optimization. If this V is already visited, right? Just continue checking all those things. It will anyway not get updated even if you leave it. But try to even keep doing this thing, right? Here also, if this U is already visited, right? Just continue the loop. Even if you don't use it, code will work, but it will take some extra iterations. Time complexity will not change. It will become 2 of whatever or 3 of whatever time complexity was there. So here, if we want to use it, when should we mark it visited? After the for loop, when we are done with all the outgoing edges or all the edges. So here we go and mark visited of U. Now this is visited, right? And then let's add the check here. visited of you, then continue. Go and remove something else from priority queue and start doing from there, right? Similarly, here we can write visited of V, then continue. Amit, you're coding, right? C++? C++ you're coding, right? You complete it. If it doesn't work, we will solve it. Mustafa? C++? Java. Java to anyway. Remember this picture. Distance of V is current distance from source to V via any path. We don't know. But if you are coming via U, then it is distance of U plus this weight. These two things we need to compare. And this comparison in any shortest path algorithm, we will keep doing this. Currently, we are learning Dijkstra's. Then we will discuss Bellman-Ford, Floyd-Warshall. This is the same comparison. If you are coming via U, are you getting smaller thing or not? Yeah, Amit, any doubt? If this U is visited, right? We don't have to repeat the things, right? While adding in priority queue, we are not checking whether this V was visited or not, right? So something may get duplicated, right? Even our here, if you add this check, if V is already visited, don't even do these things, then duplicate entries will not be there in the priority queue. Uh, duplicate edges we are talking about, right? So why we have added this? That's why even if I don't add this, things will work. That's what we discussed before this. Something, even if it is marked out, suppose it comes from the priority queue. Forgot about how we added in the priority queue. Here we didn't check while adding V, right? Whether it is already visited or not. So something to we can mark because there can be multiple edges from here to here, right? And from here also there is an edge. So this may get added multiple times, right? But if it is already marked out, we don't have to do anything. Marked out means it is already got the answer calculated, right? And this thing we are avoiding. It is already calculated, this U, right? If you see this, we should use this here also. If this V is already out, then also we should not do it, right? Like in this picture, if you remember, and that's enough. Then we will not anyway get there. From 2, there are 3 edges, isn't it? Graph wise, right? But this one we don't want to do it. Right? Even if you do it, it will not update the distance. So those are just optimizations, right? Yeah, as you are saying, if here itself this is the V this time, right? For this U, if you already checked this is out, simply don't continue with the inner loop. Then anyway, nothing duplicate will get added, right? It may get added if there are self loops, parallel edges, many things are there, right? So it's better to have that check. What does it come? And once we are done, in this problem, it says that go and print the distance array. And then let us write the code and see for something how we can trace back the path, shortest path also, right? I don't know whether I have to give new line or not. We'll check. So first time it is S, next time shortest distance, right? Whichever is the shortest distance vertex. That is not out, right? PQ dot add new edge expected bracket. Good, very small error. Variable E is already declared there. So here also I took E and then this E. So which one is easier to change? Okay. So shortest distance wise we are done, but let's this looks like this is one input graph given, right? And 0 to 5, what is the shortest distance? 0, 1, 2, 3, 4, 5. 5 looks like is the shortest distance. And in this picture, if we see what is the shortest path, distance we know is 5. Is it the same graph? 0 to 1, 1 to 2, 2 to 4, 2 to 5. Right? In total, shortest distance is 5. Let's print this. Right? We need to print this path 0, 1, 2, 4, and 5. Right? Distance calculation wise, we are done. Right? So how do we print? While updating the distance, can we print the vertex? When should we print, or should we do once everything is calculated then only? Because updating can keep happening, right? Somebody else can later also come and updates if it is not out, right? Once we marked something out, so once we marked our final destination out, then only we know which path it took, right? Isn't it? Intermediate nodes, until that node, we can print, right? So why to worry about all those things? Once our distance and parent array is ready, in last go and print it. So how do I print? We want to print distance path between 0 to 5. You are given, this is your source and this is your destination. While parent of destination, so let me take in a variable. Destination was our 5. We can start from 5, go and check who updated 5, and that way, right? While parent of this t is not equal to -1, right? -1, it will be the 0, the source. correct? We go and print this. First, let us print D ourselves. Instead of printing, D I can print. And currently it will print in opposite order, reverse order. Instead of printing, we can keep putting them in a stack, or if you write recursive code, it will automatically print, right? So while parent is not -1, do D equal to parent of D, right? And let's go and print this D again, right? So we started from this 5 we printed ourselves. Then we said its parent is 4. We will go and print 4. Then we will ask for who is your parent. It will say 2. We print 2. Then we ask 2 says my parent was 1. 1 says my parent was 0. 0 says my parent is -1. We break the loop and we are done. Isn't it? So 5, 4, 2, 1, 0. 0, 1, 2, 4, 5. That's what we traced, right? 0, 1, 2, 4, 5. Right? So maintaining just a parent array, we can also answer what was the path. Distance array will just tell what was the shortest distance. Right? Sure. Which one? Hmm. First one worked correctly, looks like, right? First test case, at least here it worked correctly. So have you used any global variables or something in Java? Let's see. This is Boolean, this is distance and parent. Distance, you put this parent and visited is false. You remove something and its V becomes your U. U with adjacent edges you got here. Then for each edge, P and W are getting. Distance of U plus P. Code looks okay. Distance is declared here, parent is declared here. And you are printing distance of I. Where you are printing? Are you printing? Okay, after the while loop. If this looks smaller, you get this. Parent anyway, we don't require, and B and distance of U. And visited of U, you are marking it. Visited of U, we should not mark it. We should mark it true here, correct? We should mark correct. Otherwise, that looks okay. NV is G dot size. Dot max value. You added here S and 0. Distance of 0 is 0. That is, this is wrong, right? Not first for S, right? And that's why when S was 0, your code worked. When S was 0, your code worked, but when S was some other vertex, right? Rest all code looks okay. So with that only this much error we got. Got? Yeah, I'll check. You submitted recently? Code is compiling? Amit. So there is an edge structure. It already has a constructor. We can directly use it. Okay. And there is a comparator written. So let's say it works correctly. Priority queue, edge, vector of edge, and a comparator. What is the compilation error? Can you read the error? I forgot which line, what error? Ah, 45, right? This E, what is this E? Data type? A structure or address to the structure? Wait, what is the data type for this? Edge. What is edge? Is a structure. It's a structure, right? We use arrow when we have address of the structure. If you directly have the structure here, right, then you use dot, right? In linked list, first node is head, but we don't remember head directly. Head is actually address of the first node, right? Root is the address of the first node of tree. If you have the address, then you do this, right? Arrow. If you directly have the structure or thing, we use it like a data member dot. But then it will not return you star. Then you have to insert a star also, right? Isn't it? What you inserted, that only you will get. Currently, priority queue, we are storing with the values directly, right? Wait, 48. Vector of edge is, no, looks okay. Oh, it is not vector of edge. This graph is created like a vector of pairs, where each pair is an integer. So no, this edge is for that. You see this definition. Graph is a integer and vector of pair of two integer. Pair is a separate class in C++. We have not used this in this notion. For creating priority queue, we used edge, but your graph is defined like this, right? Intent pair of intent. So how do we use it? Good that you are coding it in C++. Let's see. So when you ask this time it gave you a vector of pair of integers. And this is just a shorthand. We just did type def. So we are not typing this vector of pair of integers, right? With the IN, right? Now, since this is a vector of pair of integers, uh, GU, uh, does it work in C++ also for each loop? It works in some newer compiler version, but how do we iterate over this? Okay, okay. Now this adjacency list, what it will give you one time? It will not give you edge. It is a vector of pair of integers. So it will give you pair of integers as its elements. PIA. No, VPIA is a list of pairs, right? But when you iterate one time, it will give you one pair. You see this? This is a pair and there is a list of pair. If you are iterating over elements of the list, it will give you one of these things at one time. Clear? And then here, since this is pair, there is no V and W. It will become E arrow first or dot first something. It has two things. Pair is a predefined structure, first and second. I guess it will be first and this is second, right? Afterwards, you have not used anything. And it is same thing. We could have used here, but the main how it is written, it is written in VPII. You got a graph already created, right? That's why this. Ah, ah, if I go and change main code, and this is how the program should be, right? Here we are using this edge for both purposes, right? In our priority queue also we use the same thing. Graph is also using the same thing. Suppose graph doesn't show you this class or doesn't give you access to this class, right? You will have to write your own, whatever pair you are inserting in priority queue, right? So there is a comparator written for that edge. Pair we are not comparing. In priority queue, he is adding edge itself. Graph is built with pair. Priority queue is adding the edges only, and that's why it will. What happened? Okay. So again, same error type of thing is happening. First test case. So did you this zero same error? So fix it. But language syntax wise, we are clear, right? Otherwise, this is how we declare priority queue in C++. If you have to pass a comparator and all those things. Right? Here, distance of S should be 0, not distance of 0 should be 0. Source to source distance is 0, right? Next time if I pass source as 3, you will still put distance of 0 is 0. This is S and code starts working. Right? Yeah, so your algorithm conversion was okay. Language syntax wise, we had
This
stress.
conference will now be recorded.
If you are not done, submit it. And whenever you are done, you require help, ping me or WhatsApp. Let's discuss for which case this trust doesn't work. With negative edges, negative weights, this trust may give us wrong output. So see this graph and let's try to follow the distress. Let's say our start vertex is A. Don't worry about end vertex. End vertex anyway, we are calculating everything. So first time we started with 0, infinity and infinity, right? From A, there are only 2 outgoing edges, right? So C becomes 2, B becomes 5, right? Next time we will pick C, so it will update. Let's take some example where it will not update. Let's say C was 6, right? So first time with A, this became 5, this became 6, distance wise. Next time, which vertex we will pick? B, because we are picking the shortest distance, right? And from B, there is no edge going out. You see? So it will say that B shortest distance is 5. But we know that B shortest distance is 2. If you follow this path, 6 minus 4. You see this? So negative edges, if there are distress, don't use distress. Now, can you give me a real world example where negative weights will matter? I also don't know, so just discuss. weight, what are these weights? These are cost incurred, right? It may be distance, it may be time or something, right? Opposite of cost is some profit you are gaining, right? So maybe if you are traveling via this path, you are meeting some business contact that anyway you had to meet, and its gain is more, isn't it? Or a simple example, you are going from here to here, and from this road, let's say food is free. If you just take this road, and food is of 500 rupee buffet, right? So that's a negative cost for you, isn't it? This here you require 100 rupee petrol from going via this. Here also you require 100 rupee and 100 rupee, but this one you are getting a 500 rupee free food, right? So if you overall consider cost, this one is cheaper, right? Here you may have to spend those things. So negative edges, many scenarios we can have. If cost is there, then opposite of cost will also be there, right? In that case, do we agree? Distrust fails. If we just see one example, it's enough to say that distrust fails. If distrust fails, then how do we calculate shortest path? So there is another algorithm, Bellman-Ford. Bellman-Ford, we don't have to apply much mind. It's loop, outer loop. In distrust, outer loop was running b times, right? And there was a logic. We have to start from which vertex, right? It should be the minimum distance one. Bellman-Ford says that in each iteration, you have to cover all the edges each time, all the edges of full graph, and you have to at max repeat this number of vertices minus one time, and you will get guaranteedly shortest path. So let's trace it with some example, and then it will become easier. So this graph has some negative weights, so we can't apply distrust, right? Let's say we want to calculate shortest distance starting from A to all other things. This is also single source shortest path, right? We will create a distance array, parent array similar to this, right? And I guess there is no out array in this. So instead of array, I'm just writing this A, B, C, D, E, F, right? First time source to source distance will be 0. Rest all are currently infinite. Clear? In our first iteration, you have to check each and every edge in the graph. So start from each vertex and go to their outgoing edges. Clear? So how do we do? Let's start from A, then B, then C, then D. A, how many edges are there? 2. A you can reach in distance 0. B you can reach via A in distance what? 10. 10 is better. Let's update it. Similarly, F, it will become 8. By just looking at these edges, we updated those. But we have to look all the edges. Starting from B, how many edges are there outgoing? 1. B we can reach in 10 distance. So D we will be able to reach in 12. We are done with B. C, 1 edge. C we can reach in infinity currently. So let's not touch it, right? Till now we don't know how to reach C starting from A. Come to D. D has this edge. And whatever we are discussing, this is the same thing we are doing, right? This is your U, this is your V, distance of U, and then U plus W and distance of V we are calculating. That's all, right? Same comparison. So from D, this is the only edge. D we can reach in 12. Via D we can reach C now in 10. So C now became 10. Agree? A was already 0. And what about, so we are done with D edges. What about E edge? E we can reach in? No. Till now we have not reached E, right? So this edge, via E you can't reach D. E is infinity. It's not reachable. So you will not update this. Then F. F you can reach in 8. And from F to E you can reach in, right? This is one iteration. This is not the final answer. Bellman-Ford says that keep repeating the same steps NV minus 1 times. Let's do it. Again, we have to do the same exercise. A will remain 0. This edge, A we can reach in 0. And this is 10. Currently also it is 10. So we don't update it. This one will remain 8. What about this edge? B we can reach in 10. And B to D is 2. So D we can reach in 12. What is current value? 12. So we don't update it. It is already there, right? And while we are updating, we could also have marked parent things, right? Whichever updated, we mark it. Okay. After B, C edge. C edge is this one, right? This edge, if we are looking, C we can reach in what distance? C is 10. And via C we can reach B in 11. It is not better. So we leave it. B is already better. C edges we have seen. Now let's see D edges. D we can reach in 12. Via D we can reach C in 10. It is already updated. What about E? E we can reach in 9. And via E, if we now reach D, it will take 8. We got a better answer, at least for D. Let's update this. Okay. Oh, this I missed. This we covered last time. I missed this edge. At that time, E was not visible. So let's cover this time. E we can reach in 9, right? And E to B we can reach in 5. So we should update this time, right? Hmm. Hmm. Huh. No. Each edge just one time, whichever order, it doesn't matter. Next, that's why there are next iterations, right? Whatever your doubt is, next iteration will cover it, right? Right. And then E edges, both edges we covered. F current distance is 8 and plus 1 9. It is same. So we got this 9 and 8, right? How many iterations we have to do? NV minus 1. This says at max. Let's say in one iteration nothing changed. Then we can stop then and there itself. Yeah. But it says that guaranteedly, if you do NV minus 1 times, you will get the answer. Okay, next iteration. We already got a good answer for B, that is 5. A is 0. This edge will say 10, but we have 5. So we are not updating. This edge will say 8. We already have 8. So we are not updating. This edge, current B answer is 5. If we come via B to D, 7. What is the current D distance? 8. So we update D to 7, right? So now you see D path became how? From here we came, we did this minus and we came here. That is becoming D path, isn't it? Previously it was like this and this. That's why it was 12 and that way, right? Idea is clear? In every iteration, you have to iterate all the edges of the graph. Now, how do you do? Pick one vertex at a time, go to its neighbors, then pick another vertex. For each vertex, iterate all edges. All edges we have to iterate, right? That's all. Now, how do, in our graph, we stored vertex and its edges, right? Outgoing, ingoing, both we will do if it is a undirected graph, right? Otherwise, generally, edge means outgoing edge, right? If it was undirected, then this is also edge, this is also edge, but it should not matter because in graph, you have already added two edges in undirected graph, right? So if it is a directed graph, only this edge will be present in the graph, right? Yes. So obviously we have to go to outgoing edges. In undirected graph, there are two outgoing edges in both directions. Can I say? Right. Idea is clear? This one. This one. Okay. This was, we are starting here. Let's pick one by one edges. Any order doesn't matter. This edge, right? Current distance of A is 0. If you come via A to B, 0 plus 10, it becomes 10. Already there, 10 is there, so we are currently not updating it. Okay. Let's pick this edge. Why we are picking A? Because then we are iterating all the edges starting from A. Coding wise we are doing, right? Pictorially you can pick anything, it doesn't matter. Okay. Current distance of A is 0, and if you come via A to F, it will be 8. It is already 8, so we are not updating it. Then let's pick this edge. Where we are trying to reach? D. Any edge, I said, right? After A, I went to B so that I remember which edge we picked. You can pick any edge, doesn't matter, right? If you picked this edge, current distance of B is 10, right? So till here you reached in 10, and 2 you will reach D in 12. D already is 12, you don't update, right? Then let's pick C outgoing edges, right? Current distance of C is 10. From C, if you go to B, it will become 11. That is worse than this, we don't update B. Then D's outgoing edges, this edge. Current distance of D is 12, right? If you come via D to C, it becomes 10, 12 minus 2, right? It is already 10, we don't change it. Let's pick this edge. Current distance of E is 9. If you come via E to D, it becomes 8. What is currently here? 12. So that's why you updated it as 8. Similarly, when you picked this, this was 9. 9 minus 4 becomes 5. And current distance is 10. So you will update B's distance also as 5. Right? Keep doing it. You can write non-intelligent code. Your for loop always runs NB minus 1 time and you will get the answer. You can write that, okay, if you never updated anything, just a Boolean flag, right? You can break the loop beforehand also. This works with negative edges, but no algorithm will work with negative cycles. Why? So let's say something like this is there. This is 5, this is 10, and this is minus 20. You can keep repeating this and your cost will keep getting reduced, right? Some other things are also there. Let's say there is a negative cycle in between. Negative cycle means this cycle has overall, if you sum the weights, it is negative, right? 10 plus 5, 15, minus 20. Every time minus. So if you have to reduce the cost, you'll keep eating the free food there itself, right? you'll never reach destination, right? So obviously negative cycles, no algorithm will work, right? Huh. Huh. And then in each pass we have to visit just one same node twice, and then it will not be. So question is, how do we detect whether there is a negative cycle or right? If there is a positive cycle, it will never come in your answer as shortest path, right? It's better to don't go in that cycle because its cost is positive, isn't it? So Bellman Ford is also used to detect negative cycle. Let it run one more time. Currently we are running it NV minus one time. Let it run one more time and still something is distance is decreasing. It means there is a negative cycle. It will keep decreasing. So Bellman Ford is used for two cases. One, we are calculating the shortest path. If even after running this iterations NV minus one time, next iteration also something is reducing, it means there is guaranteedly a negative cycle. It will keep reducing. So we can detect a negative cycle in using Bellman. Coding wise, it is much easier than this class. No priority queue, no minimum. Is it clear? Yeah, so the example we discussed, Amit, was this one, right? A, B it will be 5 and C it will be 6. Is out. And that's what his doubt was, right? If you don't out it, the next time it may work, but we want to make it out to make it more efficient algorithm, right? Huh. Online folks still connected. Some internet issue is there. Anybody online? Can you confirm if you are able to hear us?
Yes.
Okay. So in this graph, you see there is a negative cycle from 2 to 1, 1 to 3. The total cost is actually minus 1, right? So if given this graph, if we do Bellman-Ford, then even after NV minus 1 step, one extra step we do, still it will keep getting reduced, right? And okay, see this. Time complexity good. Time complexity of this should be pretty easy, isn't it? V square, no. We are in inner loop, we are accessing all the edges. And how many times we are running it? NV minus 1 times. Right? So it becomes NV minus 1 into NE. Or V into E, can I say? Outer loop is running V minus 1 times. Inner loop, you are accessing each edges. So V into E, V minus 1 into E, exactly. But this minus 1 big O, as you will say, it is V. And since time complexity is easier to calculate, writing code is also easier, right? You just iterate all the edges and keep doing this comparison and keep updating the things, right? Okay. The third algorithm we will learn is all source shortest path. You run it and then you can answer any question. From A to B, what is the shortest distance? From B to D, what is the shortest distance? All these algorithms till now we have discussed is single source. Okay. And third algorithm, time complexity wise, it is worst, but coding wise, it's pretty easy. That's why we should remember it. Remembering is also very easy. It's called Floyd-Warshall algorithm. Have you heard about this? Floyd-Warshall works mostly on adjacency matrix. So if a small graph is given, only 100 vertices are there. Store them in adjacency matrix, run this no logic 3 nested loops, and it will calculate all source shortest path. So, and I will not be able to explain the correctness of this, how it works. Ultimately, it uses DP, but we don't need to understand this. Okay. It says that write a nested loop. First loop is your midpoint. Source to destination you are going via mid. So first loop should be your mid. Mid is 0. Mid is less than number of vertices. Mid plus plus. Next loop is start. All loops are running NV times. And that's why it's easy to remember. Start plus plus. And next loop will run for end or destination. End is 0. End is less than NV. End plus plus. So here only thing you need to remember is your first loop is via which you are coming. You are going from start to end via midpoint. This loop, even if you change ES, code will still work. Before running this, you have the adjacency matrix given to you, right? Adjacency matrix will be filled with 1 if there is an edge, 0 if there are no edge. So can I say here things will be 0 if there are no self loops? This is like from A to A there is an edge, and rest all wherever connection is there, we will have 1. Otherwise things will be 0, right? This is the adjacency matrix representation, right? If I just draw this, let us say this was ABC, this is ABC. 0, 1, 2 I'm not writing, but actually matrix is 0, 1, right? So ABC, which all edges are there? Can you tell me? A to C there is an edge. B to A there is an edge. And C to B there is an edge. That's what we represented here. If this was a weighted graph, if this is 5, B to A, this will be 5, right? Adjacency matrix weighted graph representation. This will be 5, A to C is 7, this is 7, right? So do we agree if this matrix is given, we represent the full graph, right? Yes, weighted graph. Wherever connections are there, you actually go and store the weight, and no connections are there, you leave it 0, right? Okay. It says that create your answer matrix This time we require a distance matrix, not a distance array. Why? Because this is all source shortest path. So if you are checking this one, it means from C to C, what is the shortest distance? This one you are checking from C to B, what is the shortest distance? Ultimately, it will give you answer in this. Right? How do we initialize this matrix? Copy your first weight wala thing here. So here 7 is there, here 5 is there, whatever was there. Let's say 6. These are all zeros. So you copied your adjacency matrix here, right? Wherever, apart from this, wherever 0 was there, put them infinity, right? If there is a direct edge, like from B to A, you already know it is reachable by 5, right? We may shorten it, coming via something else, but it is not infinity. If there is no direct edge, for now we put infinity. A to A, B to B, C to C, shortest distance is 0. That's why this answer is fit. Clear? This is the starting point for this. You copied the same adjacency matrix, made everything infinity wherever you found 0, and left this diagonal 0, right? Afterwards, you just check current start to end distance versus if you come via mid, which one is better? Keep updating it. So we need to compare current distance from start to end. We are comparing with, if we first go from start to mid and then from mid to end. If these terms look better, store into this. Is it clear? So how do we write? And here both of these can be infinity, right? So just you will add a if else case. If this is not infinity, then you complete. Right? But ultimately, if this distance looks smaller, right, coming via mid, then remember it. Distance of start to end becomes this new distance that we got. Simple, and we are done. Very easy to remember. 3 nested loops, all loops run NV times. Current distance of a start to end in your answer matrix versus if you go to a start to mid and from mid to end. Take care of infinity here. This may, if any of these is infinity, don't update a start to end, because infinity is always not reachable type. This variable, don't worry about what is mid here. This variable. This is a simple loop program. These are all the vertices, right? 0, 1, 2, 3. In adjacency matrix, we represented graph like this, right? 0, 1, 2, 3, right? Somehow it is connected, right? So 0 to 3, if there is an edge, this will say that 5 is current distance, right? Coming via mid, or if we are coming via 1, this becomes the mid for you. Right? Now, proof of correctness, I will not be able to explain, but you can guess that it is like DP type of thing. You started with a base cases where already you know some edges are connected, A to A, B to B, C to C are 0. Then what you are doing, you are saying that, okay, let me go one by one. If I include one of the mid point, let me again cover all start to end. If we come via this midpoint, are we doing better? This mid is any other vertex in the graph. Then include one more vertex here. M equal to 0 first you included, then M equal to 1 you included, Now we are saying if there are two choices, I can go via 0th vertex or via one vertex. Now via one vertex, it will already can reuse something. Via 0 you are coming to 1, it is already you have saved, right? So a clever use of DP, but it doesn't look like a DP, but still it is like a bottom up DP. Everything we are filling, we are reusing it. Ultimately answer will be there. Similar to distance array, we can also start maintaining a parent matrix, right? If you want to trace back the path, right? Whenever this m updated your distance, keep adding that in that matrix, right? So, and this one, it's easier to code in adjacency matrix, you see, because you have to do this. If you do it in adjacency list, then accessing this will be not order of one, right? Complexity also will increase, and coding wise also it becomes difficult, right? What is the time complexity of this? And v cube, nv cube, nv cube, but all source, all destination shortest path. So this one in notes we have shared. It's adversal. It's simple. Remember, first loop should be midpoint, then start and end. All loop are running nv times, right? And just take start to end what is the current distance, and start to mid and mid to end what is the current distance. It looks better to come via mid, update it. That's all. And by the way, there are many other algorithms, but these should be sufficient for interview perspective. Or if you are doing your own product development, you may still look for something else. Okay. Okay, let's change the topic. String pattern matching. Any questions, online folks? Shortest path. So we discussed three. If there is no negative edges, which one is better to use? Distress or Bellman? Bellman is V into E. What was time complexity of distress? V plus E log V. So this one is better, right? Multiplication we should, if no negative. Means we should try use distress. If it doesn't work, we know the limitation, then Bellman Ford we will use. If we know that graph size is smaller, 100 vertices are there, simply use flow adversal and you are done. You will not hit time limit exceeded, memory going out of bound and all those things, right? So if graph is 100 into 100, 2D array is faster, right? And since that is an array, it's actually practically faster. Array, everything is stored at same memory location, right? Continuous. So caching and everything of operating system works way better than array, than storing them in array list and all those things, right? Or maps, right? So it looks like NVQ, but for a smaller graph, we should still prefer flight version. Okay, so we learned today two algorithms. Now, Rabin Karp, KMP. Rabin Karp is easier to code, easier to understand. KMP is expert level to understand. Code is still easy, but why it works, that's why we will do some examples to understand it. So string pattern matching is a problem that many people tried solving it. There are many more algorithms. There are many more data structure also that facilitate this thing. You can solve the problem using an algorithm, using a data structure that makes it easier to write those algorithms. So suffix array, suffix trees are data structure that will solve the same problem. But today we are not building any data structure, we are just learning algorithms. So this example is one of the use case of a string pattern matching, right? In IDE, if you sort something, or in browser, if you sort something, it goes and finds wherever max is there, right? It highlights them, right? So given a bigger text, bigger string, and given a pattern to find, we have to go and find. We may have to find first occurrence, all occurrences, anything, count of occurrences. This is the broad picture of this problem, right? DNAs. This is where all these algorithms started getting invented, right? DNA is made up of 4 proteins, A, C, G, T, whatever. Only these 4 proteins are there. And this we had discussed, right? How many cells our body has? No idea. I also don't have. But 36 trillion, obviously approximately. Cell is the smallest living unit of our body, right? Or any living body, right? Inside cell, you can say that 90% of the space is void. There is something called nucleus. Just all will get filled with some liquid, right? Inside nucleus also 90% is void, and there is something, 2-3 things remain, right? But you remember chromosomes name wise, X and Y and all those things. Inside chromosome, DNA reside, right? DNA and RNA reside inside chromosome, right? And it is always chain of these things. A is connected to T, or C is connected to D, something like this, right? If you take human DNA, one DNA sample, and you store them in A, C, T, G, whatever is information, you require 10 GB file to store a single person's single DNA information. And that is stored in the tiniest nucleus of the cell. And each cell contains a copy of the DNA. So see our body, how much information we store. Right? 10 GB storage buys 10 GB long string, right? Can you guess how many characters will be there in this string? 2 power 30. Each character takes 1 byte, right? 2 power 30. So let's assume, I don't want to go there, but 2 power 30 is a very big string, very big number, right? In that, if we say that, okay, we know that this disease happens because 3 C's comes together. ACGT, 3 C come together. That's why this disease may happen to some person, right? Now you have to search in 2 to the power 30 long string. This, see how many times it occurs and all those things, right? So that's where all these algorithms getting started, invented, right? If you have a smaller text, smaller string, you do brute force, doesn't matter, right? But if you have data very big, then you have to devise some faster algorithm. Otherwise, you will keep searching, right? So our DNA is a text, and pattern is something given that you have to search. How many times it occurred, where it occurred, and all those things. How many times ANA occurred in this? Nine or eight? 1, 2, 3, 4, 5, 6, 7, 8, 9. Here in interview, you should ask, should I count these two as separate thing, or because this A you are sharing with 2, right? So answer will differ. If you counted this, you are not allowed to reuse it again, then only 8 times. If you are allowing overlapping A, then it appeared 9 times, right? So problem is clear. Given a text, T, and this T is sufficiently large. That's why we are learning these algorithms, right? And a pattern P, find the occurrence or occurrences of this pattern in this text. What is the brute force way of doing this? Choose a window. Which window? Size of the given pattern. That much window you take here and you start comparing characters one by one. If it matches, that is your best case, first window, order of one. If it doesn't match, move to the next window, right? So next window is this, isn't it? Keep moving like this, and each time you are doing in S of I and P of J, you keep comparing, right? What is the time complexity? If text was N, pattern length was M. Exact time complexity, tell me. N into M, I know big O is. Exact practical time complexity. N minus M into M, still not correct. Of For matching or discarding one window, we obviously require M things, right? M comparisons. How many windows are there of M size?
n minus m plus 1 into
Almost
m.
correct, not correct.
N minus m plus 1 into m.
N minus M plus 1.
Yeah.
Plus 1 minus 1, I also keep getting confused. An easier way is simply draw. If your array had, let's say, 5 things, how many windows are there of 5 size? 1. So 5 minus 5 plus 1. How many windows are there of 4 size? One is this, another is this. So 5 minus 4 plus 1. Agree? No need to remember, always take a small example and do this. But always doubt on this plus 1 and minus 1 in any algo you are writing. Right? So it is n minus m plus 1, and in each window we are, in worst case, we will check m things, right? M or m minus 1 things, right? Because if m things matched, we are done. No, last one, after checking also, we know that it is not matching. So this is the exact. But big O wise, let's say if m is really small, then all those things, it becomes n into n. Okay. How do we optimize this? Brute force, we can solve it, right? How do we optimize it? Mhm. Uh, no match. Okay. Okay. Very good. So one approach we are getting is, let's say ABC is there. Here we were matching something AX, whatever, right? If it doesn't match, then again start comparing from this A, right? Because our pattern is not starting from A. Why to even start matching from here? We can directly move to this window, right? How we will move, that we need to learn. But this is looks like an approach. There were n minus m plus 1 windows. If we skip some windows by some guesswork or some knowledge, that this window will certainly not be my answer, right? Then we will reduce the time complexity. Clear? That's one approach that KMP will take. No, it will. KMP and all those things are worst case is still bad. Amortized or average case is order of n, n plus n. N into m, it will make it n plus m. So let's see. Second approach is, in brute force, we are matching these window, right? Window with pattern. So if we make this match faster, quickly we know whether it matched or not. Currently we are taking M comparisons, right? What if we start matching them faster? So two ways to optimize the things. Leaves out some window or make our matching algorithm itself faster. Currently, our matching algorithm is brute force, right? Each character we are checking. So can you guess how we can optimize this matching? Still, we have to check what will be there. If you move, then still if this is different, right? You still have to match it, right? Hash or something. If we can create the hash, generate hash of pattern, generate hash of that window, and quickly check if both hashes are equal. We'll see the details of it, right? But the concept is hash should be getting calculated quickly, order of one, then only it will benefit, right? Okay. So Ravi,
What if we do XOR of some kind?
XOR of some time. So whatever we are discussing is the how do we generate the hash. Agree? You do XOR, you do summation of all ASCII codes, you do multiplication of all ASCII codes, right? Isn't it? Ultimately, we want to make it faster. XOR or of everything, if you do, then still it will be M each time, right? Next window, still you have to do XOR, right? We have to choose intelligently. How do we generate hash quickly? That's all.
No. We don't
Yeah.
have to do it n times again and again, right? So let's
Okay.
say we did XOR for the first 6 characters. Now when we need
Yes.
to do the characters, XOR of characters from second to, let's say 2, 3, 4, 5, 6, 7th. Yeah.
Yeah. Yeah.
So we can do XOR of the first character again. That would nullify its effect. And then we
Very
can
good.
just add the XOR of the uh, recent character that has been added in the window.
Very good. Very good. And that's what we need to learn, right? So what he suggested is first time we calculated XOR of this, but next time we don't have to do XOR of full, right? XOR this, it will nullify it, right? And then add this one or whatever was the next character, right? Clear? This may be one potential candidate for hashing. Let's see whether it works or not. How do we know that this is a good hash algorithm, XOR or whatever? Works for all the cases. Nothing is perfect. So, no, time complexity is here. We are saying after first iteration, it is order of one, generating next hash. Very good. Even if the order of characters are different, ABC, CAB, BCA, XOR will always give the same hash, right? Getting it? So in hashing terms, what do we say this? This is collision, bad hash, and because of bad hash, many collisions are occurring, right? There are 20 keys, all are generating the same hash. We want to minimize this. We can't avoid this. Agree? Clear? Okay. So how many of you can read Greek alphabets? Alpha, gamma, delta, epsilon,
Epsilon,
zeta, eta,
theta, theta.
eta, iota, kappa. And after we use mu and lambda, right? So many means almost related to English, not so many. So let's say we choose this slide for a purpose because we wanted to discuss that. Let's suppose our alphabets had just 10 alphabets, our language, right? This is the pattern we need to search in this text. One easy way is simply add the ASCII codes or whatever code we have for those things, right? So what will be the ASCII code here? Theta is 7, beta is 1, and delta is 3. For simplicity, let's say this is the hash generated. What we are doing, we generated hash for the pattern. and this hash will be valid for all the matches, right? Pattern is not changing. Then go and generate hash for first window, right? And next time, how do we generate this? This is what Prakash was mentioning, right? Subtract 7 and add this 4, isn't it? In 11, you are removing this 7. So for all next windows, hash generation is order of 1. Agree with me? But as he was saying, this leads to a problem, right? ABC, CAB, PCA, everything will have the same hash. If hash is matching, then we check the pattern whether they are actually same or not, because hash can still match for two different keys. Key 1 is also same, key 2 is also same, still we got the same hash. When hash matches, then we have to actually go and do brute force for whether it is the correct thing or not, right? But we want to minimize this collision, and we know that this is a bad choice, right? If our pattern is 3 length, 3 factorial, or 6 keys will be there that will have the same hash, isn't it? Even more than that, 3 plus 2 or 4 plus 1, still the sum is 5, right? More possible collisions will be there for a given sum, isn't it? But something of this sort we require, where we do some mathematics and next hash we generate it quickly. Idea is clear? So XOR plus, these are the starting point, but we see that many collisions will occur and ultimately will keep matching more number of times. So it will be nearer to NM than nearer to N, right? Rabin Karp suggested that instead of summing them, use it like a number. Our number system, 10 decimal, right? If this is this, then this and this will be 251. Right? No match. Means still something will collide, but chances we are minimizing too much, right? So number creation, this time how you will create this number for pattern? You take first ASCII, multiply it by 10, next ASCII, keep adding it, 21, multiply it by 10, next ASCII, keep adding it. So 215, this way you create it, right? But the question is, how do you create the next rolling hash? So how do we create this hash? Yes. So whichever mathematics you do, but do you agree that we can still create next hash in order of 1? 215 we already know, hash of the previous window. I can do 215 modulo 100 and I'll get 15 plus 2 digit, I'm expecting, right? 15 into 10 plus new digit, right? So next hash calculation, or I can do, if I remembered this anyway, we will remember where is our current window, right? I can divide it by 2 into 10 to the power m minus 1, where m is the length of our window. So you divide, you got 15, 15 into 10 plus this thing, right? So we minimize the collision, we still retained the property of generating next hash in order of 1. And that's what Rabin Karp suggested. Rest all is easy code this time, isn't it? When hash of your pattern and this match, you write another loop of actually checking whether they match out. This was for a number system or alphabet where only 10 things are there. Rabin Karp suggested that if it is a DNA, ACGT, then base of your number system will be 4. Right? So 2 into 4 to the power 2 plus 1 into 4 to the power 1 plus 5 into 4 to the power 0. Right? If only 2 alphabets are there, it becomes binary numbers. If we are considering English alphabets, 26. So only thing changes is wherever we are doing 10, we'll replace it with 26. Rest all logic will remain the same. How many characters are there is given in the pattern, right? Correct. Hmm. Hmm. In English, yeah, and that's why we discussed we need to know how many alphabets we are dealing with, right? Let's say we are dealing with all ASCII characters. How many characters are there? 256. So your base becomes 256. No, no, they will give you, right? Or take it 256, max possible thing, right? Size of the character set or your alphabet that you are alphabet. When I say alphabet, it is the character set, not actually one ABC. It can contain equal to whatever is your ASCII characters, right? We take it as a base, right? Clear? So something like this. You take the ASCII code and whatever base is there, 26, 52, 100, 256, right? You keep generating a number like this. Generate a hash. So first time we generated hash for pattern, it will take order of m. We generated hash for first window. It is again m, right? Then our loop will run n minus m plus 1 time for each window. Pattern hash is already calculated. Next hash you are calculating in order of 1. If pattern hash and window hash matches, then you are writing m comparison. If it doesn't match, in order of 1, you are moving to the next window, right? Worst case wise, if you really care about worst case, it is still nm, right? Let's say each time hash is matching. Uh,
I don't see how it will match every time.
it may not match, but if something is given, or let's say we have to find all the occurrences, right, of A and A,
Okay, yeah, then it's possible.
all the occurrences of A. So worst case is worst case. In this case, this is matching. Next one is also matching, and when it matches, you don't know whether it matched because actually it is matching or hash was faulty, right? So in this case, it is still n into m, right? But if you take a random string or a normal paragraph or something, this will still do better than brute force.
One question here, Ashutosh.
Yeah,
If we
yeah.
are considering this ASCII code that you just that we just saw,
Mhm.
multiplication and creating a number, then in
Yes.
what case will the hash be default? I mean faulty. For every new pattern, there will be unique hash, right? So let's say we took the example of 215, that is gamma beta
Uh,
zeta.
uh,
215 will not be generated in any other case, right?
it will
So,
get generated because ultimately it is we are doing 21 into 10 plus 5, right? Now, can't you do x into y plus something, still you get 215? We may get, let's say this is also 0, this is also 0, here itself 215 is there. Chances we are minimizing, but sum of few numbers is
okay,
not
yes,
going to be unique, right? We can get
yes,
multiple numbers whose sum is the same answer, right?
yeah,
Got it?
that's
Chances are
true.
minimized, but do you agree here if your x was 0 and z was 215, still you will get the 215, right? And not in this example. I'm saying summation wise, summation you can get with multiple options, right? Here also it is multiplication and summation, right? 2 into 5 was there versus 5 into 2 sometime came. Still you will get 10 and something, right? So chances are there. And you can think of, I don't want to spend time there, but obviously collision will occur sometime. And in any hashing collision, if doesn't occur, then you are wasting something. String has numbers also, that's what, then you will base. So numbers also has a ASCII code, right? And the numbers also keep it. Yeah. Numbers ASCII code you take. ASCII code, I am just saying ASCII code, some code you have assigned to them. That's all. Right? You very good. If pattern is very long or window size is long, we may cross the integer limit. Right? And that's why we do it modulo of some prime number. And modulo we learned, right? You will not do modulo of just here. You will keep doing modulo wherever you are doing some plus or modulo p here also, modulo p here also. Right? So actually we use modulo wala thing. So good that we raised. Right? Hashes always works with modulo because it can be long. Or if pattern is not long, 256 itself is the base. 256 to the power 7 itself may start crossing. I don't know. Right? Yes. Take that as a code. It is not saying that use ASCII code. Right? Take anything as a code. Just assign this character as this code, this character as this. Right? This one is done. This one was easy. Right? Okay. So Rajnikant says when my code fails to compile, the compiler apologizes. So let's say in this string we are searching for computer, and this is what Amit was saying, that here COMP matched, I and U are not matching. We know that I never occurs in computer, right? So even if I check this window, it is not going to match because this window also contains I. So we'll never find the pattern, right? So it's better to avoid some of the windows. Isn't it? Getting the idea? We should start comparing from starting from here. Now, human wise, you see that this is also not matching, but in array you will go one by one, right? We skipped this I because I was not there in our pattern. So obviously nothing will match. From here, there are chances that it will start matching. So we avoided 1, 2, 3, 4 windows comparisons. Hmm. Yes. CI. Hmm. We can align with that. Yes. Yeah. So idea is clear that we want to avoid some window, right? Now, based on that, there are many algorithms that avoids because it notices something is not there, something is there. It avoids because something is common here, something is common here. They may combine 2, 3 ways to avoid the windows, right? KMP wise, it doesn't do this. It does the alignments. So let's see the KMP. But the idea is clear. We want to avoid some window. In each window, still we are going and comparing the things, right? Now you can guess that while we are comparing the things, can we combine hash comparison also? But since you avoided the window, the rolling hash calculation, either you will still doing it continuously, otherwise it will take time, right? So KMP says that first time text and pattern here mismatch occurred. Till here everything was matching, right? Now do we notice that this and this are same? That's what you are suggesting to me, right? So if we start matching from here, there are chances that things will start matching. This and this we know that these are same. We will see how we will know this. Visually, we are able to see those two are same, right? This is the prefix of pattern, and this is the suffix of in the text. Till now, whatever we have matched, right? So what KMP says that if we align our I and J pointers, like I was telling which character we are matching, J was telling which character we are matching. These two, if you pre-computed and know that these were the same characters, you don't even need to match these two things. Start matching from this star. We avoided this window. We avoided this window. Two windows we fully avoided. Third window we started, and in third window also we avoided matching two characters. Pictorially, you got what we did? Yeah. So in our pattern, till here everything matched. IJ, SI and PJ, SI and PJ. Here it didn't match, right? So next time brute force white, it says that go and match this, right? Right. Now KMP wise, somehow we will be able to see that this pattern and this pattern are same. End of this and a start of this are same. Then matching will happen from here, right? There may be a chances that match can occur. How we will know, we will come later. Pictorially, we are able to get, yes. How we will know, that is the complex part, right? But if this prefix and this suffix are same, let's align like them. And we know those are same. We will pre-compute something. So we know that these are same, start matching from here, right? And if things matches, good. Otherwise, keep moving on. So we avoided matching this window, third window we chose, with which we are saying that there is a chance that something will be there. In third window also, we avoided matching first two characters, animation wise. Okay? So how much we have to shift? MP says that you have to calculate something called LPS, length of longest prefix, that is also suffix. Now let's take some time to digest this. What are all the prefixes of this string? A, AB, ABA, ABAA. It says that always consider proper thing. Proper means it should not be the same string. So we'll ignore the same length prefix or suffix. What are the suffixes? A, AA, BAA, and proper wise, it's not one, we will leave. What is ABAA, you are saying? One suffix is this, another suffix is this, another suffix is this. Suffix means it is ending with that, right? It is not a substring. No, we are not only considering the prefix that is of the length of same of the given string. So here actually prefix wise ABA is also a prefix, and here also ABA is a suffix, but this one we are not considering. That's all. We should take. I just listed down all the prefixes, proper suffixes. Then we check anything common is there. A and A is common. That's all right. Where is ABA? ABA, we never took it. We are just taking proper prefix and suffix. If you take it, then always your answer will be that. Because string, prefix and suffix is same. If you take the full string, right? That's why we ignored it. Agree? There can be many things common. You have to take the length of the biggest common string. The longest common prefix, that is also a suffix, right? And let's see The intuition is coming here because of this. In this window, this was the prefix, that was the suffix of whatever we matched till now. If we know that two things are common, we know that two things we can ignore and let's align from there. Clear? This pre-computation we need to do. Let's do it manually. Then we will see how we can code it efficiently. Obviously, we can code it brute force way and you can calculate the things. But we want to do it in order of n type of thing, right? Then only it will benefit. We will create a failure table or prefix table where we will note down what is the longest common prefix that is also a suffix of string A. A, how many prefixes, proper prefix it has? Nothing. How many suffix it has? Nothing. So what is the common max length? 0. For AC, proper prefix is A, proper suffix is C, nothing common, 0. For ACA, 1, common thing, A. So you can treat it as a prefix suffix, or you simply say what is the longest bordering element. That is also here and there pictorially, right? Border. So now tell me, how do we fill? This is 0, this is 0, this is 1. What about ACAC?
2.
2. And what is the border? AC. If we just do A is there, AC is there, ACA, 3 proper prefixes, C, AC, CAC, and AC is common. This is the only common thing, so longest comes here is 2. What about ACACA? Here we will also consider overlapping, ACA and AC, 3, right? What about next one? Full string, 4. 4, ACAC from left side and ACAC from right side. So longest common prefix that is also a suffix is ACAC. And notice that it is not like a palindrome. What is the border here? Just A. It's not like AB and BA is the border, right? But if here AB was there, then AB is the border. Overlaps are also allowed. Manually, we are able to do it. So let's check this one. First one will, can I say first one will always be 0? Right? And by first one, we mean that, or by this entry, we mean that what is the longest common prefix that is also a suffix if our string was this only. That is the information we are storing. This entry stores the longest common prefix suffix for full string. Why we require this? Because anywhere mismatch can happen, right? Before mismatch only data we have to check. We'll trace it. Fill this table. First one is 0, 0, 1, 2, 2, wrong. 4, no.
0.
0, right? There is no common border, right? Here D is there, here D is not there. So how is it? Right? It is 0. Right? If you want, trace all the prefixes, suffixes, and you will see. Right? In each suffix, D will come. In no prefix, D will come. Right? So nothing common will be there, right? Okay, what about this?
One,
Order is 1,
2,
2.
0.
Order now becomes this and 0. Clear? We will build this table. This will help us skipping some of the window. So let's first learn the algorithm. Assuming we already got the code, how do we build this table? Okay. So a text is given, a pattern is given, we have to find it. First step of KMP says that go and build this table, and table is for pattern. So let's build the table again manually. 0, 0, 1, 2. What is the border here? ACA. Okay. 0, 0. Everybody able to see this? So let's see, we got this table filled. How do we use it? We take two indices I in a string, j in pattern, right? I will start from 0, j will start from 0. We start matching, write a loop and start matching. Ultimately, at this position ij, we found first mismatch. Here, here we see where mismatch occurred, its previous string. ACA. What its LPS length? 1. It says that one length border is available. Obviously, this and this still here, everything is same, right? You're getting this intuition, right? This table told us that, okay, one length thing is a prefix in this, that is also a suffix is whatever you saw till now in a string. So how should we align so that this comes here and next match should start happening with when C and T? Which pointer we should send? If this was I, this was J. J should come here at C position, right? First thing first, how did we got this coding wise? 1. Where was J? Which index? 0, 1, 2, 3. Which entry we went and checked? Second entry in the array, right? So we go and check J minus 1th entry because we want LPS for this part, whatever matched till now. We went and checked J minus 1th entry. If it gave us 1, we know that one thing is matching. Here, one length border is there, right? Here A is there, here A is there. So let's align like this, that this A and this A will come below, and next matching we should start doing from here. So J should come here, right? I will still be here. Where J came? Which index? No? 1. 1. And this you code wise you will see 1 is what this table suggested. J minus 1th entry, whatever table is suggesting, just move J there. We will trace it again. Got this? When J moved there, in animation it moved, but actually J simply moved, right? What happened? You started matching from here. This you already know that they were matching because prefix suffixes we are same of one length, right? You ignored this window. You ignored this window. You ignored this window. You are still checking, but first character you ignore. Clear? So idea wise we are clear. We are skipping something, some windows. In Windows also we may skip some more characters. And then this time let us trace. Again mismatch occurred. So A, what is its LPS length? 0. Obviously, if single character is there, 0. We said whatever is LPS length, let's move J there. So J becomes A. Again start matching. Mismatch occurs. J is already 0. Slide, move to the next character, right? From here it will not match. So now which pointer moves? I. I becomes I plus j is already 0. Where it will? Picture wise. Code wise, j is still 0. I becomes I plus plus, isn't it? Agree? So picture wise pattern is moving, but j is still at 0. I became I plus plus. Again mismatch is occurring. J is already 0. So I plus plus. This time I and j character are same. Move. I and j character are same. Move. These are not same. Mismatch. Go and check what is the border for AC. Visually also we know there is no border for AC, right? So j will come at A, 0. Or you go and check. Here also it is saying 0, right? So A comes at 0. This time again mismatch occurs. J is already 0, I plus plus. And that way you keep moving. Ultimately, if found, you will get it. If not found, you will reach the end of things. Your I will cross or J will cross, right? Hmm. Ah, ah, ah. It's up to you. You can break here, right? Your if I reaches here, after this you should break the loop, right? Huh? Means length minus m time or m plus one something, right? Anyway, it is not going to match because that length itself is not there in the string. Agree? Let's trace it with multiple examples. Otherwise, and once we see this animation, remember this, then coding will become easier. We are going and checking in a table. Either we are moving j, we are moving I, and all those things, right? So leave this. Let this side works. If this works, we will trace some other examples. So understanding is important. I don't know who will ask KMP. And there are better algorithms. KMP is actually one of the best algorithm for general cases. Algorithm wise, data structure wise, suffix array is one of the best. Once you created a suffix array and there are algorithms using in order of n, you can create a suffix array. Once you are created, you can answer at least 1,000 questions type for a string. How many times it occurred? Suffix array has an answer. Where it occurred second time, suffix array as an answer. What is the longest substring? That is a palindrome, suffix array as an answer. Those things you will learn if you are interested in competitive programming. Otherwise, it's of no use. Two strings are given. What is the longest common substring? Suffix array has the answer. And all answers after pre-computation of ON, suffix array returns in OM. Once the data structure is built, just pattern length, you will know the answer. Similar to try. Suffix array is also an advanced try, nothing else. So in try, once you build the try, then if you are looking for a pattern word, right? You just require car, you just check CAR is there or not, 3. So similarly, if suffix array or suffix tree is built, we will be able to answer many things. So it depends for which system we are solving the problem. If we have to answer many things, better to build suffix tree type of things. Characters are visible to you font wise. Online folks, so anyway, let us see. And this you can try yourself. I'll share the link. But let's see 1-2 more time animation and then we will have better understanding. So if this is the text, this is the pattern. What is the first step? Build the table. So we will build failure function and pause it. Now let us build ourselves and then we will tell me C0, CT 0, 0, 1, 1. CNC only, right? CT and CT 2, 0, 0. So 1, 1, 2, 0, 0. So 1, 1, 2, 0, 0. Right. Now how search happens is, let's see. Search. Okay. So first time CNC matched. So what we will increase? I or J? Both. I plus plus, J plus plus. T and T match. Both. Skip a step forward. T and T matched. Both. C and G mismatch. You will check the LPS for CT. CT is 0. So J will become what? 0. Clear? Again, C and C are matching. A and T are not matching. J is currently 1. You will go and check the 0th entry is this table. It is 0. So J becomes 0. Right? This time A and C are not matching, but J is already 0. So what do we do? I plus plus. J still remains this. Right? Then C and C matched, T and T matched, G and G, C, C, T. Here mismatch occurred. So for T, it is 2. So J becomes 2, 0, 1, 2. J will come here. So what we are saying is this CT and this CT, we are aligned. Getting the idea? And then next match will occur from this G and G. So this T we check 2, and that's why J came here. And next time you start matching from here itself, because wherever J was there. If it matches, good. If it doesn't match, you hit the boundary. If it matches, you have to find all occurrences. Still, you will move ahead. Is it clear? Approach wise. Now it looks scary, but let's see the code. Now KMP, once failure table is built, it should be easy to implement, right? Whatever we discussed, that was the algorithm. So if text I and pattern J are same, I plus plus, J plus plus, isn't it? I plus plus, J plus plus. If mismatch occurs, this is the failure table 0, 1, 2, 3. Agree? 0. Here border is 1 triangle. Here border is 2 triangle. Overlapping. Here border is 3 triangles. Right? Here mismatch occurred. So we go and check J minus 1 entry. Right? So in else case, J equal to failure of J minus 1. We moved J there. If J is already 0, if J is not 0, we go and check. If J is already 0, then I plus plus. Right? That is the algorithm. Right? This one we are doing if we have to find all occurrences. Right? If J equal to pattern length, you found the one occurrence. Break if you just have to found. If you have to repeat, then J again move to its LPS. building the failure table code. That is the hardest part, it looks like currently, right? This one we understood. You feel comfortable that you can code it. And that's why we discussed this exact same code will work for building the failure table. It will use some DP. Almost exact same code we will use for building the failure table. We built failure table manually. We understand what is a failure table, right? Using failure table, we saw that writing this code, following the algorithm is easy, right? Now let's discuss how do we use some DP so that we can build the failure table in order of n, where order of m, where m is the length of the pattern. If we don't do, then we have to generate all the suffixes, all the prefixes, keep matching, it will be more than m, right? So to DP wise, we will try, DP wise, we try to reuse something that is already calculated, right? While we were filling the failure table, we also are filling from string is single character, 2 character, 3 character. One by one we are filling, right? So let's see if we can reuse something. Suppose this was the current border of this string. Okay. Currently the string is this. Next you are calculating one extra character, right? First we calculated for, let's say, ACCA. This is our, but do we know that what is the current border? 1A. Next, what is Y2? Palindromic wise, we should not see. Currently this is A only, right? A is the border. AC and CA are different things, right? Okay, so we already know that this is 1. Now let's add C here. The next string is this, that we are calculating failure table. Can we reuse this? That's what this rule is saying, right? Whatever new character is coming, here also if this is the same character, right? Then AC and AC will become the new border. So if this C is the new character, luckily here also C was there. Then we extended the border length by +1. You don't need to again go and calculate this border length, right? Agree with this? So we used previously calculated things in some cases, at least, isn't it? Recursively or one by one, we are going and filling it by looking into previous border. So let's see how it will work. So currently this is the border. Agree? For full string, this is the border because prefix and suffix both are same. Now let's say one extra character we are adding, we are building failure table because we are building failure table incrementally. First A, then AB, then ABA. So this is the next character in the given pattern. If this character is red, then +1 happens. Whatever was previous length and this one. Which character we are checking here? Bit index. So here length is 9. 4 plus 4 plus 9. We are actually checking 9th character index wise, isn't it? And anyway, we know whatever is the new character index. So we check if pattern of failure table of, you can ask this string, right? Whatever is the current character -1, right? This failure tables entry, you go and check which character is this, and this character, if they are same, simply put +1 there. Picture wise, is it clear? So now you see this became the border. but it may not be always the case. Still, it will improve some complexities. Clear? Second rule says that, and this is the hardest rule. Is this the border of this full string? No, no, right? It is like a palindrome, right? Let's say this section also you are seeing like this previously. This is the border full. For this border, if this blue was border, for that border, if this was border, right? Border means here also the same blue is there, right? Then here also the same blue is there, because we know this full string is a border of this, right? Pictorially, let's see some examples and we'll. Are you clear? So if A is a border of B, then A is a border of this side also, right? This was, let's say this was full border. Don't go into color. Inside this border, if this part was a border, it means here also same thing was there, right? And we already know that this is a border, it means both are same. So here also same thing is there, right? How do we use it? So let's focus on this string. Till now failure table, can we verify 0, 0, AB, ABA, ABA, ABAB, ABAB. So let's say till now we filled this somehow, right? If X comes here, it becomes 5, right? You went and checked fourth entry in this table, 0, 1, 2, 3, 4. Agree? This was the previous rule. If Y comes here, 0. So these two cases are clear. What is the current border of this string? 4. And what is the border exactly? ABAB. In ABAB, what is the border? AB. So rule says if we are not able to extend the full border, can we extend this smaller border? What character can come so that still we will be able to extend this AB? If A comes here, then ABA and ABA is the border, right? So recursively or iteratively, whatever, discussion wise recursively, if we are not able to extend the full border, check borders border. Can you extend it? Complex, right? I don't know how people thought this. I mean, they thought it many years ago. It's not 2019, right? But agree, if A comes here, we are going and checking this. And okay, ABA is, this character is same, then directly we can do what this, how did we increase? What I should write here? ABA is 3. But how did we wrote 3? Border length was 2. AB border length was 2. We increased it. So 2 became 3. Borders border length. If that is also not the case, again go to its border until it becomes 0. Approach wise, is it clear? Coding wise, I said that it is same as KNP. Combining these two rules, we will see that algorithm calculates this prefix or LPS table in order of n. By the way, don't worry about this. Tell me what was the time complexity of our this code? Ny. N into m. In which case n into n? Okay. In every match, last element is mismatching. Okay. So let's take an example. Everything is A, and we are searching for, let's say, A, B. Then we will directly jump. You will start skipping this, right? And this may be the best case. Okay. So you can try calculating the time complexity, but did we ever moved I backwards? I we are always doing plus plus. J, how many times we moved backward? Whenever there is a mismatch, maximum is how much times I already moved, right? Is and J already moved or I, same thing, right? So it will be maybe 2n, but it will never be more than, right? I is always moving forward, right? J, even if it comes back, it is covering the same distance, right? In we are visiting the characters only once, agree? Main string wise. J is coming backwards, but if you think carefully, J is coming how much backward? Whatever distance I traveled. And I we are saying is I will travel just the n distance, right? So J, even if it is duplicating, it will cover 2n combined, right? It is not n square wala thing. Intuition wise, just think. Otherwise, it's harder to calculate the complexity because we are moving backward and forwards, right? Agree? Okay. So I'll show you this code, understand. And this is the LPS calculation code, almost similar to that code. Character. This which diagram? This one. Okay. Correct. Yes. Very good. Yes. So if it is a red, this full border got extended. If it was a black, then borders got extended. But not green. I'm saying if this was black, then this 4 green, 1 black, 4 green, 1 black. This is the because of second rule. If you are not able to update border, update border. Go and check if it is there. But if it was green, wait, if it was green, so, right? So previous border was this. We know that this is not green. Border was this. We know that this is not green, right? Then go to border. What is the border here? 3. 3 greens here, prefix, 3 greens here, suffix. This is the border. Is this green? So we are able to reuse this thing, right? Too much intelligent thinking, whatever. And but once you learned this, you will be able to somehow think and correlate some other problems. Right? Now This picture clearly shows that borders also matters, right? We don't want to calculate everything ourselves, right? So code wise, it is almost similar. Whatever we discussed, it is coded. This one. Length is remembering what is the length of the current border, right? If the new character coming is at the length, are we able to extend it? Then length plus plus, we are storing it. If we are not able to extend, then go and check its previous border length, length minus 1. And again, keep checking whether we are able to extend or not. I leave this. If you trace this, you will see that whatever we discussed, that is the algorithm. And again, in this, we are always moving forward. So it will be 2m. It will never be more than that. Approach wise, one by one, we are building. Either we are taking help of DP, or we will directly say, if nothing mismatch is happening, then it will be 0. If nothing is matching, right? So 2m time, we will be able to build it in worst case. Okay. Now we have 5 more minutes. One more thing, since we discussed suffix array, let's discuss. It will also revise our try concepts. Suppose this is our string, and we want to solve the same problem where ANA is there or not. How many times ANA is there? These type of problems we need to. We are now building a data structure. Suffix tree says that obviously we need to build tree for suffixes. What all suffixes it has? Here proper also, not proper also we are taking, right? It says that treat these are different words. All suffixes are a word for you. Go and insert them in a try. Now you will see the beauty. If you insert them in try, let's build the try. Root is empty. First word, how do we insert a? Ath link points to a new node, right? Sorry, this should be red, this should be green. A is a word, right? NA from here, no, NA, a new link will come. Here, all the words starting with A, we can go down, like apple will come here, but NA, we require a new link, right? So this is your N link, and from N, A link is come. And this is green. ANA, from A, N comes, AN, and one more A comes. Sorry, this should not be green, right? This is red. Pictorially, although we don't do it, but this is the concept for suffix tree. Now, if I ask, is ANA a substring of this or not? Just see ANA. In try searching is just checking 3 things. Length of the pattern you are, right? Why this works? Because any substring is, and now this is a code, any substring is prefix of a suffix. Digest it. Any substring is prefix of a given suffix. We stored all the suffixes in a data structure that makes us easier to find prefix. Try is also called prefix tree. That's why we use it in auto suggest. See the beauty of this? Now you can extend this. If you build this tree, you will see that A in A, and if you add this A in A, NA will come here, right? You ask how many times A and A occurred. You come till A and A and see how many branches it has. How many, there you will go, it will give you a count. You can also start storing the index where the word is ending. And that will give you where that pattern you found. Right? So this data structure, whenever you get time, just learn it. It will give you a practice for try also. And it's a beautiful data structure. Right? Suffix tree is nothing but try for all the suffixes of the given word. Now we don't do this like this. There are Ukkonen or some algorithm is there using which you will be able to build this in O of n time. Even it looks like scary, but conceptually it is a try. Okay, guys, then we will stop here. Today is the last class. One more thing I keep forgetting. Star of the week. So this time, I remember Rajesh and Yojit, right? Anybody else who's tried doing it yesterday? No? So no need to update. Huh? Oh, last week you did 6,000 or what? Oh, huh. Okay, but still you have to make progress. It's not that you are at the top. It means okay, okay. Okay. So we have this time. What is this? Bluetooth speakers. Ah, ah. Right. So data structure. In memory. In memory. All data structures are always in memory things. Mhm. Then data structure is sorry, all the events are there in DB, right? When your server comes up, it loads everything and builds a try and keeps it in memory. That's how it works. Data structure is same data loaded in memory. If you store it, you will not be able, whichever thing, linked list is there. In DB, it is just a record, right? If you load and store it in memory, we call it a data structure, right? How, and that's why we use caching and all those things, right? We don't want to access DB much more. We load many things in memory so that it becomes faster, right? While loading itself, why don't we build a try so that it becomes easier to sort also, right? Otherwise, this question will always be there. BST, even if you build, why for try? BST, how do you store in DB? You don't store BST. You just store the numbers, right? Right. Now, DB itself, if you index something, when you say that this column, go and index it, DB builds that data structure for you. And for you, it looks like, okay, this is something magical, right? But ultimately, DBMS is doing for you, right? And Yojit, last week also, your is pending, right? Anybody else whose gifts are pending? Online folks, any questions?